So in this video, we're going to look at the definition of Laplace transformations. So first of all, what are Laplace transformations? Well, Laplace transformations transform complex equations into simpler ones that are easier to solve. So this is heavily used in higher level engineering, physics, math. And I know it's going to come up again for me when I get into my aerospace engineering classes very shortly. So this is why I'm reviewing it. I know it's going to come up again, and I know it's a very powerful tool to understand. So I'm revisiting it now, and let's get right into it. So the definition of the Laplace transformation is the definition of it. There's later on we're gonna use like it's called like it's like a table. I guess you kind of memorize or just use the table to get around using the definition. But it is highly important to understand the definition of the Laplace transformation. Highly important to know how to do it, because you could be asked how to do. I know I was, for example, on exams, quizzes, I was always asked a question to use the definition of Laplace transform to do it. So I'm going to go over the definition of Laplace transform in two steps, in two videos. This video, I'm just going to look at what is a piecewise continuous function, because for the definition of Laplace transform, the function that we are transforming has to be piecewise continuous. Okay? So, what is a piecewise continuous function? You might already know, and if you do, go ahead right ahead and skip this video and go to the next one, because I'm going to go over everything about piecewise continuous functions. So, for a function to be piecewise continuous, it has to be continuous on each subinterval, and it has to be defined on discontinuities, if there is any. And I came up with this little example, I think it'll work for what I'm trying to get at, where we have x squared. Let's go ahead and graph this. We have x squared from 0 to 1. So it'll look like this. And we have 1 plus t from 1 to 2. So that's going to start up here, right? And that's not defined on 1. So it's going up. Okay, so it's going up 1. So that's going to be 3. From 1 to 2. Is it piecewise continuous? Is it continuous? Okay, well, it has to be continuous on each subinterval. Is it continuous from 0 to 1? Yes, it is, right? Is it continuous from 1 to 2? Yes, it is. Continuous on, well, I should say continuous when x equals 1? No, right? Because there's a jump discontinuity there. It's not continuous there. Is it defined on 1? Yes, it is. So it's defined on the discontinuities. If we have something like this, that's not piecewise continuous. This is piecewise continuous. So I have a few examples down here to do exactly this. So this problem, it asks for determine whether I have all three of these I'm going to do, 1 through 3. Determine whether f is continuous, piecewise continuous, or neither on the interval 0 to 3. So let's go ahead and graph the function like it asks us. So t squared from 0 to 1. Oh, it's just like we just did, right? From 1 to 3, right? 2, 3. T squared from 0 to 1. That was awful. That's better. T squared from 0 to 1. Now we have 2 plus t from 1 to 2. So that starts at 2 and goes up 1. So we're at 3 here. Right? And then it's going plus t, so it's a slope of 1 until we get to 2. Oops. Like this. That's closed because of the less than or equal to. So now we're here. We have 6 minus t. Oh boy. So how can we figure out the slope of that one? Well, when t is equal to what? 2? That would be 6 minus 2 is 4, right? So it starts at 4. And we're going down 1. So it looks like this. I'm going to try to make that look even. And that's included. Okay. Is it continuous? Oh, first of all, it asks first. In this case, determine whether f is continuous. Is this function continuous? No. There is a... Not... let me do that. F isn't continuous. Because x, when x equals 1, we have a jump discontinuity. Not sure if I spelled that right. Piecewise continuous. Oh, it wants to know if it's continuous, so it's not continuous, so it isn't continuous. So we know that, so we can rule that out. But now we can look at, is it piecewise continuous? Well, let's see. Is it continuous on the subintervals, right? So 0 to 1, is it continuous? Yes. 1 to 2, is it continuous? Yes. 2 to 3, is it continuous? Yes. Is it defined on the discontinuities? Yes, because if we have f of t, f of 1 is equal to 1, right? Because of this right here. So it is defined. So yes, this function is piecewise continuous. Next one. Same thing, t squared from 0 to 1. I'm just looking at that second one there. I don't even know how to draw that. Let me think about that one. 1 over t minus 1. 1 over t minus 1. So, let me think about that. So if we have 1 over t minus 1, if t equals 1, so it's going closer and closer to 1. So that tells me it's kind of looking something like, oh, okay, I see. Yes. So t can't equal 1, so we're going to have an asymptote here, right? For this particular section. And it's going to go towards 1, like this. Yeah. Until we get down, it's going to start over here, it's going to go towards 1 this way. Something like that. It's going to get closer and closer to 1, but it never touches it. Unless it might. No, it doesn't. So we have a discontinuity there, right? Yeah. Yep. So we're going to have a discontinuity there. And then we just have 1 from 2 to 3. Well, that's easy. It's just this. So this is okay. So this first one's continuous, and the second one is continuous, right? And obviously it's not continuous at 1, right? So the function itself isn't continuous. But is it piecewise continuous? Well, these first two are. Remember, we have to take the limit from the left and the right to determine if this one is. Right? If we're looking at this one, the limit from the right, well, let's look at it as it approaches 1. The limit as it approaches 1. Oh, yeah. If you're looking at 1, the limit as t approaches 1 from the left, right? That would be 1. But from the right, it doesn't exist. So it's not continuous at 1. And this isn't continuous. So this one here is not continuous when it goes to the right. So this one can't be continuous here. So this one is not, the whole function is not continuous, and it's not piecewise continuous. Right? Because that is not continuous. So it would be neither in this case. Now we have one more example. Same thing again, t squared. This textbook just loved that. One from, oh, that's easy, right? From here to 2, 1. We have 3 minus t. We'll add 2, that would start at 1, and then go down 1. Like this. So this one, the whole thing's continuous, and the whole thing's piecewise continuous, right? No discontinuities anywhere. Everything's defined. Yeah. So I would say this one is piecewise continuous. Continuous, piecewise continuous. I guess it just wants to know continuous, right? Determine whether it's continuous, piecewise continuous, or neither. So you can see that this one is continuous. This one's neither, and this one is piecewise continuous. But this one will still be piecewise continuous though, right? Okay. So that's it for this video. Pretty simple. Just went over what is piecewise continuous. So in the next one, we're going to look at the actual definition and actually using it to take our little functions here and transform it into something easier to use. All right, so see you in the next video.